All right, so today I want to talk about projectile motion. So projectile motion is a really important application of 2D kinematics. So we're going to spend quite a bit of time on it. And projectile motion comes back unit after unit as like an add-on topic. So a projectile, by definition, is any object upon which the only force acting is gravity. So when we looked at free fall in one dimension, objects that are in free fall are projectiles. But we tend to represent projectile motion as the most general type of motion, which means that we have not just 1D motion, but 2D motion. So our projectile motion means that we project the object. So it's free fall after being launched with an initial horizontal velocity. So I picture free fall, just basic free fall, as just the object falls straight down. So there's no horizontal velocity. Whereas if I want to think of projectile motion, my object has some initial horizontal velocity. So it's still going to fall, but it's also going to move horizontally as it falls. And so it's going to take a curved path. So what's really cool about these two problems is that if I were to release this one horizontally from the starting height and this one at rest from the starting height, they're actually going to hit the ground at the exact same time. And I've linked a video that shows this in Canvas, right after this video in Canvas. So I might take a moment here and pause and go watch the projectile motion ball drop versus ball launched. It's really cool, and you'll be able to see kind of how that works. But these are actually going to hit the ground at the same time, as long as there's no air resistance or anything. So how there's easier problems, there's harder problems. Because even though this says like it has to have an initial horizontal velocity, it could also have an initial vertical velocity. So I could also do examples where like I throw it up at an angle. And in that case, it has both a horizontal component to its initial velocity and a vertical component to its initial velocity. And so that ball would go up and then come down. I could have objects that start at the ground and go up and come back down. I can have them thrown from like a cliff or some height. There's all sorts of different possibilities with this. But what I wanted to look at right today is just understanding the mechanics of how this works. So just like we did with free fall, we're always going to assume that time starts immediately after the object leaves the source of whatever is giving it its initial velocity, the hand, the cannon, the bat, whatever it is, and that time stops immediately before it's caught or it hits the ground, because we can only have gravity as the only force that's acting on these. So those are some assumptions that we have to make. So basically our same free fall assumptions we have to make with projectile motion, because projectile motion is just a different type of free fall. So what we're going to do is we're going to look at an example of a cliff and a cannon. So I'm going to have a cannon here, and I'm going to have this projectile here for this cannon. So essentially what's going to happen is I'm going to give this projectile some initial velocity. And let's say that it's launched purely horizontal, and it's launched from some height above the ground. So I have an acceleration that is downwards. The way that this acceleration due to gravity is, my acceleration, and I'm going to define my downward direction as negative, so my upward direction is positive. So my acceleration here is going to be negative 9.8 meters per second squared. And actually, I'm going to do this with just 10, just to simplify this down. So my acceleration due to gravity is going to be approximately negative 10 meters per second squared, because it's going to be in the downward direction. So in this case, in all of these cases, the only force acting is gravity, and gravity acts in the vertical, so the only acceleration I have is in the vertical. So this acceleration in gravity is the acceleration for this motion. There is absolutely no horizontal acceleration anywhere in projectile motion. Yes, internally there had to be some sort of horizontal acceleration to get this projectile to its starting velocity. But since we're starting time at the instant it leaves the cannon, we're assuming that there is no horizontal force acting. The only thing that's acting is gravity, and that's in the vertical direction. Now, what this means is this means that for every 1 second time interval, my speed is going to increase by 9.8 meters per second in the y direction. Actually, it's going to be 10. I'm rounding this to 10. So in the y direction. So what that means is initially I have no vertical velocity. So this v0 is just equal to vx0, because vy0 is equal to 0, because I have no vertical component to my velocity. Now what's going to happen is I'm going to create an acceleration, and I'm going to add essentially 10 meters per second worth of speed. Now let's assume that I started here at 20 meters per second. So I had an initial horizontal velocity of 20 meters per second. But after 1 second, and that's, so here t equals 1 second, what happens is I'm going to add negative 10 meters per second worth of vertical velocity. I'm going to do vector addition here. And so my resultant velocity is going to cause my ball to kind of follow this curved path on average. So it's going to be here now. So it's going to move to that position. It's going to drop by negative 10 meters per second. Well, in the next second, it's still moving horizontally at 20 meters per second. I have no horizontal acceleration, so my horizontal velocity has to be constant. And my vertical velocity was negative 10 meters per second, but I have to add on another negative 10 meters per second. So I'm now going negative 20 meters per second. And I now realize that those were not very well drawn perspectives. So I'm going to shorten these, try and make it a little better. So this is now negative 20 meters per second in the vertical, because I've been accelerated 1 more second. So I've added another negative 10 meters per second. So my object is now here. Well, in the next second, I'm still, so this is after 2 seconds. In the next second, I'm still moving horizontally at 20 meters per second. But I've now had 3 seconds. So I'm now moving vertically at negative 30 meters per second. So I'm now at that position there. And then horizontally, in the next second, I keep skipping writing my seconds down. I was moving 20 meters per second horizontally. I'm still moving 20 meters per second horizontally, but now I've had 4 seconds to accelerate vertically. And so now at this, I'm going to hit the ground here at 4 seconds, or just before 4 seconds. And I'm moving at negative 40 meters per second. So my velocity vectors are changing directions, and my overall velocity is increasing. And if I were to be able to keep this going, this would actually take the shape of a parabola. If I were to keep this kind of going, it doesn't quite work quite, I should have given it a bigger horizontal velocity to make it a little clearer. But this is going to make the shape of a perfect parabola. And we're assuming here that there's no air resistance. Once again, time starting when it leaves the object and right before it hits. So what happens is that our horizontal velocity is constant, our vertical velocity is constantly changing, and so we're going to end up with a changing speed. Now, what this means is let's say that I had a plane that was here, flying above the cannon. There's my plane. Flying above the cannon. And that plane was moving at 20 meters per second. If that plane was moving at 20 meters per second and stayed a constant 20 meters per second, that means that that cannonball always stays directly underneath the target, underneath the plane. So at all points in time, the tip of that plane is in this line with that. So this is really cool because this is actually how they do airdrops. Well, it's a little more complicated because you have to take into consider air resistance and wind and so forth. But basically what you do is like a bomber. I watch a lot of World War II movies. So if I am in a bomber and I need to drop, let's say it's pamphlets, and we're not dropping a bomb, let's just say it's pamphlets, and I wanted to drop a box of pamphlets or a box of relief food supplies, and I wanted to drop it because I'm in an area that I can't get it, and I want to make sure it gets where it wants to go. Well, if I drop it here, I will be directly over the target at the same time that the package hits the ground. And that is really cool and powerful. And that's actually what they had to do. And they had to do all these calculations by hand, plus adding in things like the general air wind velocities and different things for that. Now, this same process happens even if I don't have a horizontal launch. So if I were to have a vertical launch, I get the same kind of process. I still have the same conditions here, but let's say that I'm launching here with my cannon up at an angle. So now I'm going to have some initial horizontal velocity and some initial vertical velocity. So I'm going to have some V0 that has both a horizontal component and a vertical component. So let's just assume, for simplicity's sake, that the horizontal component and the vertical component were both 20 meters per second. So that means that my initial velocity would have been about 28 meters per second. That's just using the Pythagorean theorem. So if both of those are horizontal, that gives me my initial velocity. So now what happens? So the same thing happens. So in the next instant, so what happens is that as it's moving in this direction, it has its own velocity associated with it, but I'm going to have this acceleration due to gravity. And that acceleration due to gravity is going to pull and cause a change of -10 meters per second. So that at the next instant in time, it still traveled 20 meters per second to the right, but now it's only going at 10 meters per second vertically, because I was going 20, but I slowed down by 10, so now I'm going 10 up. Well, in the next second, I'll still have gone 20 meters per second to the right, but I will have slowed down by another -10 meters per second. So basically at that point in time, I reach essentially the top of my path, and my vertical velocity is 0 at that point. My horizontal velocity is 20 meters per second, but my vertical velocity is 0. Well, in the next second, I'm going to speed up again by negative 10 meters per second. So, but I'll still have gone that 20 meters per second. So I'm now here. In the next second, I'll be going that negative 10 meters per second plus another negative 10 meters per second. So I'll be going negative 20 meters per second. And if I did this right, oh, I forgot to go horizontal. 20 meters per second. So that would be here. And if I did this right, that should magically be at the exact same launch height. At this point in time, I'm going negative 20 meters per second, and I'm going downwards at 20 meters per second and to the right at 20 meters per second, which means my velocity at this point is 28 meters per second. Well, the same thing was happening over here. So just like when I toss the ball up and it comes back down, at this point in time, I'm going to have 0 net displacement at that point in time. And I'm at the exact same speed I was at this exact same height. So I've gained height and then I've lost the same amount of height, so I'm with the same speed, but my direction has changed. So then I'm going to go negative 30 meters per second and 20 meters per second horizontally. So I'll now be here. And then I'm going to go negative 40 meters per second because I've increased and accelerated more. But I'm still going 20 meters per second to the right. And so on and so forth until you hit the ground. So in this case, we would have hit the ground somewhere between whatever these time periods are. And if I were to trace out the path of this, I would once again make a parabola. Well, that one was a little large. I would make a parabola. So I have this parabolic motion, and remember that when you solve for a parabola, if this was a function of time, that there would always be 2 corresponding times, 2 velocities to 2 corresponding times would give me the same position values and so forth. And that's because it gets mirrored here on either side. So that's kind of how projectile motion works. So the most important kind of things we have to remember is at the very top, our vertical velocity is 0. Our horizontal velocity is equal to whatever our initial horizontal velocity is. Our horizontal velocity is always there. So at no point in this motion does it come to rest. If I were to toss it straight up and then down, all of its velocity would be 0 at the top, because there would be no horizontal velocity if it goes straight up and straight down. So if I toss the ball straight up and then straight down, at some point in its motion, it has to come to rest. If I throw it at an arc, at no point in its motion will it come to rest. With this, if you have some sort of initial angle here, your Vx0 is going to be the adjacent side, so that's going to be V0 cosine theta, and your Vy0 is going to be V0 sine theta. So you can find the magnitudes of those if you're given your initial velocity, or if you know one of these, you can find your initial velocity. The distance that a projectile travels before it hits the ground we call the range. Not to get confused with domain and range in math, where range are y values. The range is basically the horizontal distance that's traveled by the object. You have pure symmetry anywhere where you're on one side or the other, where you'll have the exact same speed, but the speeds will be in different directions. And if you're working a position thing here, like maybe this is the ground, this is a perfect parabola. So the time that it takes to get here is exactly half of the time that it takes to get over here. So this portion will be perfectly mirrored. If you're all above the ground and you've got this extra here, it won't perfectly mirror, but your time up and your time down, if you're going between the same heights, will be identical. So that's kind of our basics of projectile motion. Horizontal acceleration is 0, vertical acceleration is -g. And that's because we're defining the upward direction to be positive. We generally set y equals 0 to be the ground and y equals h maybe to be our starting height of some different type of things. So we're defining that as positive. You don't have to do it that way, but if you are setting y equals 0 to be the ground, then your acceleration has to be -g. I could also define y equals 0 to be my starting height, in which case this down here could be y equals -h. That's still defining the upward direction as positive. But if I define y is equal to h down here, then I'm defining my downward direction to be positive, and my acceleration would have to be positive. So you have to be very careful with your vector directions. So that's kind of conceptually what's going on. We'll get to the mathematics of how to solve these problems. It's a lot of systems of equations as we go through. All right, have a good day.